In this first item on the test, we have a truss where we've been asked to find 3 different member forces. Notice that that is conveniently located so that we can come and cut all the way through one panel or one section of the truss, and it'll expose all 3 members that we're interested in. And given that we have a simply supported truss, pin on one end, roller on the other, that's going to also tell us that we are going to have to find one of the reactions. So if we go over to A, we'll have 2 at the pin, in AY and AX, which will be in this very simple case, because of the roller being on a horizontal plane, that we will have the trivial answer that AX is equal to 0. The only one we're going to really need is AY if we look ahead here, and if we were to cut through that panel to the free-body diagram we see down below, the beginnings of one, we'll easily see that we'll be able to find out what the 3 member forces are without having to find both AY and HY. So that's how we'll proceed here, is only finding AY by summing moments about H. Let's take clockwise as positive and walking right across on the structure from left to right. Notice our distances from HY, the moment arms for each of the forces, are 3, 6, 10, 14, and 18. So we have a plus 18 times AY minus 18 times 1 minus, then the next force is 2 at 14, and then the next force is also 2 at 10 meters, and then we have at the peak the 1.75, it is at 6 meters, and then we have the last one, we'll set that equal to 0, and we'll find out when we solve for that AY is equal to 4.5 kilonewtons acting up, as we would expect. If we were to sum moments about A, we would find out independently that HY would equal 4.5 kilonewtons also acting up. The sum of those two would be 9 kilonewtons, and sure enough, 1 plus 2 plus 2 plus 1.75 plus 1.5 plus the 0.75 would give us then the total downward force of 9, so we would have equilibrium independently there, the way we would want it to. So let's get the reaction of AY down here on the lower free body diagram, and we want to get these 3 member forces. BD in this situation we've learned is oftentimes in compression, so we'll assume it is pushing on the joint. We'll CE bottom chord we will assume is in tension. CD is not always so clear what it might be in the specific case, so let's just assume it's in compression and see how the math will play out as we go along. And let's see, we can some moments is usually in a method of seconds our most powerful friend. If we sum moments about point D, we'll get rid of both BD and CD, and it'll leave us only CE. So let's start there. Summing moments about D, let's take clockwise positive again. We'll have 4.5 minus 1, so a net of 3.5 acting up, spinning around D in a clockwise fashion, and that moment arm here is 4 plus 4, or 8. And then we got the 2 going in the opposite direction at 4 meters, and then we'll have CE. Now CE here is down along the bottom chord, and we're taking the moment arm here perpendicular to the line of action of the force, and that's going to be then at 4 high. And that's what we see over here as well. So we'll have minus 4 times CE, set that equal to 0, and we'll find out that CE equals a plus 5 kilonewtons. Now the plus means that the way we showed it in the free body diagram is correct, and so therefore we find out that CE equals 5 kilonewtons in tension. Right, next then we can sum moments about point A. When we do that, we get rid of BD and CE. And let's take clockwise positive. So the 1 and 4.5 go away, BD goes away, CE, so we only have two forces. And so we'll have 2 times 4. And then notice that CD is at an incline, so we could break that up into two different components if we wanted to, or we can go back and recognize here that the horizontal distance from C to D is 2, the vertical is 4. That means our ratio is 1 to 2 to square root of 5, and so we want the y component of CD, and that y component will be that vertical part, so that's 2 over the square root of 5 times CD. That's the y component, and its moment arm then is the 4 plus the 2 are 6. And we set that equal to 0, and we'll find out that CD is equal to a minus 1.491. So that's shown in compression, it's pushing on the joint. So what we really have just figured out is that it has to be going in the opposite direction, and so 1.491 kilonewtons, and it will turn out to be in tension. So we had compression, that becomes the opposite to give us that result. And then finally we've got, let's see, we can sum moments about, we've done about A and D, let's do it about C. That gets rid of CD and CE, and we can get BD then. And let's take counterclockwise as positive this time. And we'll have, in that case, we have a net of 3.5 going the opposite direction. So we have that at a moment arm of 6. And then plus the 2 kilonewton force times 2 meters. And CDCE go away, they pass through point C, but we got to get BD in its X and Y components. So let's do the X component. That'd be, let's see, square root of 5, that's 1 over, it's the flatter one. Well, we got to get this right here. So as we take this down, we've got 2, 1, square root of 5. So if we want, right, the vertical component would be 1 over square root of 5 times 2, and then the horizontal component is 2 over the square root of 5. It also has a moment arm of 2, and so now we set that equal to 0, and this will be a big negative number, goes to the other side, and even after we subtract off that 2 times 2, we'll find out that BD is a positive 6.34, or therefore BD equals 6.34 kilonewtons acting as shown, which is compression. And there's your 3 answers.